Hello everyone, we're going to look at another electronics and networks question, a bit of current analysis, I'm sure it says circuit analysis. So the question is asking us to find the current in R2 using three methods, equivalent source method, nodal analysis method and mesh method. So this is our circuit. We've got a current source, a voltage source and four resistors. 1, 2, 3, 4 currents going on, and then we have all our values of our current source, our voltage source and our resistors along here. So if we look at the first one then, A, equivalent circuits, let's see if we can get these in side by side. So an equivalent source, if we have a current source with a parallel resistor, we can switch that into a voltage source with a series resistor. It's simple Ohm's law to do the conversion. So if we're from current to voltage, our voltage source is going to be our current source times the resistor, and the resistor will remain the same value. So to solve this particular problem, we're going to take this circuit and we're going to manipulate it so that we only have resistors in series. So what we're going to do is calculate the current through the series line, if you like, and it's all going to be the same. So I2 is going to be the same as I1 and I3 and I4 because they aren't going to exist anymore. So we're going to split them up into our two circuits. So we've got one circuit here that has a parallel resistor and another circuit here that has a parallel resistor, and my goal is to get rid of those two using our source method. So if we start with circuit 1, we can convert the current source to a voltage source. So we've got our current and our resistor, and we're just going to use Ohm's law to find out our voltage and our voltage, and we're going to convert that into a voltage source. So we've moved that parallel resistor now, so we have a series resistor here and a voltage source rather than a current source. 56 volts. Now you might see that I've used 7 times 8, and that's milliamps times kilo ohms. So if we look at 7 times 8, that's our 56. And it would be the same as 7 times 10 to the negative 3 times 8 times 10 to the 3. That will give us 56 as well. You can put all the values in if you don't feel confident, but if you keep everything in kilo ohms and milliamps and volts, you can just simplify it by just using the values and not having to put the extra times 10 to the 3 in. So we've sorted circuit 1 very easily in one step. We've just converted our current source to a voltage source. So the next on our circuit 2, we're going to convert our voltage source into a current source. So we're actually going to add a second parallel resistor in. So we're going to take this voltage source with our series resistor, change it into a current source and have another parallel resistor. So all the resistors stay the same value, so we've got R3 which is a 6K and R4 which is a 3K. So to find our current source value, it's going to be our voltage source, which is 42 volts, over our R4, which is this one, which is 3K, and it's going to be 14 milliamps. So we've got a current source of 14 milliamps, and then our two resistors. So now we're going to combine the parallel resistors using our standard 2 resistor in parallel equation. So we've got 6 and 3, we end up with a 2K resistor. So we combine the two to get a 2K resistor. Now if we convert the current source to a voltage source, that puts the resistor back into series. So 14 milliamps 2K, Vs equals Is times R, 14 times 2, which equals 28 volts. So we've got a voltage source of 28 volts and a 2K resistor. So now if we combine the circuits, if we put circuit 1 and circuit 2 back on, our new one, we end up with this circuit. So we've got our voltage source and our resistor, we've got our voltage source and our combined parallel resistors, then we've got our R2, what we were trying, and this is where we were trying to find the current in R2. So we can calculate as follows. So the current, or I2, is equal to the voltage over resistance, Ohm's law. So we're looking at the voltage drop here, so we're going from 56 volts to 28 volts. So 56 minus 28 is actually 28. And then we're going to have the voltage drop across our total resistance. Because they're in series, we can just add them. 8 plus 4 plus 2, 28 over 14, and we end up with 2 milliamps that goes through R2 using equivalent source method. Right, let's look at the nodal analysis to work out 2 milliamps. So nodal, we're going to be looking at E1 and E2 and E3, maybe not. So node E1 here, so we're looking at IS coming into E1 is equal to I1 plus I2, so that's Kirchhoff's current law we're using, and IS will stay as IS, it can't be anything else. Our I1, we're going to convert it into, from the current in, we're going to use Ohm's law and have the voltage over the resistance. So we've got voltage at E1 over R1, so IS is equal to E1 over R1, and then I2, we're going to do the same here, Ohm's law. I2 is going to be E1 minus E2, that's the voltage drop across the resistor, over R2. So E1 minus E2 over R2. So we've got IS, which is 7, so 7 is equal to E1 over 8, which is the value of R1, plus E1 minus E2, the voltage, over 4, which is the value of R2. So if we multiply both sides by 8, that's going to remove the denominators from the equation. So we're going to have 7 times 8 is 56. 8 over 8 is going to be 1, and they're just going to cancel each other out, so we just end up with E1. 8 over 4 is 2, so we end up with 2 times E1 minus E2. So next we want to multiply out those brackets, so we end up with E1 plus 2E2 minus E1 plus 2E1 minus 2E2, and then if we just add those two together, we can end up with our first equation, which is 56 equals 3E1 minus 2E2. So now if we look at node E2, let's get the drawing back up here. So we're looking at I2 is equal to I3 plus I4. So I2 we know from before is E1 minus E2 over R2. We know we'll be able to work out that I3 is E2 over R3, E2 over R3 plus E2 minus E3, or E3 is VS, so we can say E2 minus VS over R4. So we plumb in the numbers for the resistors and the voltage as well. So we've got this over 4, E2 over 6, E2 minus 42, which is VS over 3. And we're going to multiply both sides by 12 to remove the denominators. So 4 times 12 ends up being 3, 6 times 12 ends up being 2, and 12 over 3 ends up being 4. So that's 12 over 4 is 3, 12 over 6 is 2, 12 over 3 is 4. So we end up with 3 E1 minus E2, 2 E2 plus 4 E2 minus 42. So we multiply out those brackets, we end up with 3E1 minus 3E2 equals 2E2 plus 4E2 minus 168, which is your 4 times your minus 42. So next we're going to add our E2s together, and then we're going to subtract 6E2 from each side. So we're going to end up with 3E1 minus 3E2 minus 6E2. So we end up with 3E1 minus 9E2, which equals minus 168. So that's solved for E2. Well, that's the equation for E2. What we've been able to derive from this particular node. So if we solve for E2 now, quite nicely, equation 1 has 3E1 and equation 2 has 3E1. So if we subtract them two, the E1s pretty much disappear, they cancel each other out. If this had only been one E1, we could have times this whole equation by 3, would have had to times the 1E1 by 3, the 2E2 by 3 and the 56 by 3, but we don't need to. So we've got equation 1 minus equation 2. So we end up with 0E1, which disappears in the next one, and then we have minus 2E2 minus 9E2, which ends up in plus 7E2. And we also have 56 minus 168, which ends up in 224. And try that on your calculator if you're not understanding that. So we end up with 7E2 equals 224. Divide both sides by 7, E2 equals 224 over 7, which equals 32 volts. So we've got 32 volts at E2. So if we solve for E1 now, and this is because we know if we've got E1 and E2, we can work out the current going through R2. So we're going back to equation 1, and what we can do is where we've got an E2, we can plumb that number in. So 3E1 equals 2E2 equals 56. We plumb our 32 in instead of E2. So we can work out that 3E1 minus 64 equals 56. Add 64 to both sides to move it over this way. We end up with 3E1 equals 56 plus 64, which is 120. Then if we divide both sides by the 3, we end up with E1 120 over 3, which is 40 volts. So we've got, so let's solve for I2. So I2 equals E1 minus E2 over R2, which we worked out at the beginning. So we've got 40 minus 32, which is 8 over 4, which is our R2. 8 over 4, our 2 milliamps. Now let's look at solving I2, or the current through R2, with mesh analysis. So mesh 1 has only got one current in it, and that is IS. So mesh 1 equals IS, which is 7 milliamps, and that 7 milliamps will just run through R1, that's fine. Mesh 2, so mesh 2 is going to have M2 R1, M2 R2, and M2 R3 as it runs round, and that will be opposed by M1 R1. So as M2 R1 goes this way, M1 R1 will go this way. And it is also opposed by M3 R3. So M3 R3 goes this way, and M2 R3 goes this way. So we end up with M2 R1 plus R2 plus R3 minus M1 R1 minus M3 R3. And then the sum of everything is going to be 0. We've taken account of all the current in here. So we plumb some numbers in, we end up with M2 8 plus 4 plus 6. Again, these are all killers, that's fine. Our answer is going to be in milliamps. And then we can put minus 8M1 minus 6M3. Multiply these, add these up. 18M2 minus 8M1 minus 6M3 equals 0. Then just rearrange them to get the minus 8M1 at the front, 18 plus the 18 M2 in the middle, and then the minus 6M3 at the end. Mesh 3, so we're going to have M3 R3, M3 R4, and that will be opposed by M2 R3. So M3 R3 goes that way, M2 R3 goes this way, opposing it, and that's going to equal our voltage source. So we end up with M3 R3 plus R4 minus M2 R3 minus our 42 volts, and that's because it's going in the opposite direction. We're coming round this way and that's going that way, so we end up with a negative 42 volts. So we add our numbers in and add them up, and we end up with 9M3 minus 6M2 equals 42, and we just rearrange them to get our M2 plus M3. So now that we've done our mesh analysis, we need to now look at what we're going to do with them. What we're going to do is we're going to solve the value of M2, because that's going to be our current through R2. So we've got our three equations here. M1 equals IS equals 7 milliamps. Then equation 2 minus 8M1 plus 18M2 minus 6M3 is 0, minus 6M2 plus 9M3 equals minus 42. So we solve for M2 now. Now we're going to, because we know we have a value for M1, we're going to replace M1 with the value 7 milliamps from equation 1, and we're going to put that into equation 2 to get a fourth equation. So this is going to help us get rid of our M1 in this equation, so that we end up with two equations that just have M2 and M3 in it. So this is our equation. We substitute in our 7. We then multiply that out, and we're going to then times both sides by 56, so we end up with 18M2 minus 6M3 equals 56. So that's our equation 4. Now to find M2 we can use equations 3 and 4, that's these two, and these only have M2 and M3 in it. So what we need to do is we need to cancel out the M3s. So we're going to multiply the equations so we have the same number for M3, and then we're going to remove it. It doesn't matter whether they're positive or negative or mixtures, because we can add or subtract the equations depending on what signs they are in order to eliminate our M3. So we can see that one equation has 9M3, the other has 6. So if we use the value 18, as that's in the 6 and 9 times table, we can multiply our equations to both have 18M3. So if we times equation 3 by 2, we end up, it's got 9M3, we end up with minus 12M2 plus 18M3, which equals minus 84. We take equation 4 and times it by 3, as it has 6M3. We end up with 54M2 minus 18M3, which is equal to 168. Now we add these two together because we've got a positive 18M3 and a negative 18M3. So 18M3 plus minus 18M3 is going to end up with 0M3. But we're going to end up with minus 12 plus 54M2. It's going to give us 42M2. We have minus 84 plus 168, which is actually going to be 84 again. And then if we divide both sides by 84, we can work out that M2 is 84 over 42, which is 2 milliamps. Thanks.